Europa isn't just an icy moon of Jupiter. It's one of the most dangerous and fascinating places in our solar system. Imagine a world covered by ice thicker than mountains, with hidden oceans underneath that have more water than all of Earth's seas combined. The temperature there is so cold it freezes you instantly, minus 160 degrees Celsius. But it's not just the cold that would kill you. Europa sits inside a radiation field so strong it would destroy every cell in your body in seconds. And there's more. The gravity is so weak you could jump as high as a building, but the lack of air would make your blood boil inside your body. Scientists discovered something even scarier. Beneath this deadly ice, alien life might be swimming in dark oceans. How can something live in a place that would kill a human in just 5 seconds? Subscribe to the channel, leave your like and comment what part of the world you're watching from, because now I'm going to tell you everything. What does a day look like on a moon that always keeps the same face toward its planet? Europa moves around Jupiter in a path that stays at about 670,900 kilometers from the giant planet. This distance is close and steady enough that Jupiter dominates Europa's sky. Farther out, both bodies circle the Sun together at about 780 million kilometers. That great distance sets the scale of the light that reaches the ice. It is a quiet fact, but it shapes every scene on the surface. Europa turns once on its axis during each loop around Jupiter. This lock means the same hemisphere always faces inward toward the planet, and the opposite hemisphere always faces away. Because of this lock, one full day on the surface lasts about 85 hours. Sunrise takes its time, noon lingers, and night stretches for many hours. The rhythm does not rush. It repeats with dependable regularity. A point on the ground sees Jupiter in almost the same part of the sky every time the sun climbs and sets. The slow pace and the fixed gaze toward Jupiter are a direct result of the way Europa spins and orbits. A body's size shapes how gravity behaves at its surface, how curved the horizon appears, and how much area the crust covers. Europa's radius is about 1,560 kilometers. The face that looks up at space is a shell of water ice. It is bright and sends much of the sunlight back into space. The surface does not swallow light easily. The ice acts like a pale mirror on a planetary scale. Because of that, the ground does not soak up much energy during the long day. When light fades, the brightness also means the surface loses heat efficiently. These basic optical features are not only visual qualities. They control the energy budget at the very top layer of Europa's skin. The way Europa moves under Jupiter's pull fixes a simple map in the sky and on the ground. One spot on the surface always faces Jupiter. Another spot always faces away. One side leads as Europa moves along its path. Another side trails. These 4 directions do not drift. They hold steady year after year. This fixed geometry helps define regions for study, for navigation, and for planning. It also means that patterns tied to Jupiter, such as tides and the direction of incoming particles, keep returning to the same places on the ground. The lock does not end variety, but it keeps the basic layout stable. A long day of about 85 hours changes how time works for any visitor or robot. Work and rest periods do not follow a short cycle. They follow the sky. If a task needs sunlight, it has a wide window at local noon but must wait a long time if it misses that slot. If a task prefers darkness, it enjoys a long stretch of night but also must plan for deep cold that lasts. Instruments that depend on shadows or on glancing light can aim for very low sun angles that persist for many hours. Cameras that benefit from light near midday can schedule image sets when the sun is high and the scene is brighter, though still dim compared to inner regions of the solar system. Nothing on Europa rushes through dawn and dusk. The long transitions allow deliberate timing. The lock also shapes the view. Stand anywhere on Europa and Jupiter does not sweep across the sky in a rapid arc. It hangs in a fixed region and drifts slowly over the long day. On the inward-facing side, Jupiter is always present. On the outward-facing side, it never rises. Stars and the sun move with the same slow pace as the ground turns under them. This steady sky simplifies navigation by sight and by instruments that track known targets. The path around Jupiter is more than a route. It is a metronome that sets the tempo of light and darkness, tides and quiet, and the recurrence of surface stresses. Each orbit brings the same sequence of events back to the same regions. This repetition is useful. It allows teams to predict when light will fall at a given angle on a named ridge, when a shadow will cross a valley, and when a slow tide will flex a crack. With timestamps tied to this clock, observations from different passes can be lined up with precision. Scale matters for design as much as it matters for science. A radius of about 1,560 kilometers sets Europa's curvature. The horizon lies closer than on a larger world. A low ridge can hide a large area behind it. Communication lines need clear sight from a lander to a relay, and the curve of the surface limits that sight. The small scale also reduces the speed needed to stay in low orbit, which helps a spacecraft plan a brief pass. At the same time, the small radius leaves less room for safe orbital paths that avoid harmful zones near Jupiter. Careful geometry turns into longer life for machines and more complete maps for science. Distance from the Sun, the lock to Jupiter, and the bright face of the ice together control the surface energy balance. At about 780 million kilometers from the Sun, sunlight is weak. The bright ice returns a large share of that weak light. The long day does not make up for the low input and the high reflectivity. The ground stays cold even in full light and cools fast when light fades. This is not only a number in a table, it becomes the foundation for every thermal decision on or above the ice. The lock sets up a simple language for locations. The inward face is the sub-Jupiter side. The outward face is the anti-Jupiter side. The side that points forward along the orbit is the leading side. The one that points backward is the trailing side. These names help avoid confusion and help plan repeatable paths across the surface. If a line on the ground curves across the leading side, a second pass months later will see that same line under almost the same lighting and the same orientation to Jupiter. This is not a trivial convenience. It is how global mosaics gain consistency and how change detection becomes reliable. The long day stretches operations for any platform that uses solar power. Sunlight is dim, the day is slow, and the night is long. Power systems must store enough energy to bridge many hours without light. Thermal systems must keep sensitive parts warm through long darkness. A steady, predictable rhythm helps here as well. A fixed schedule of light and dark allows precise energy budgeting. Engineers can plan hours of work under light, hours of sleep under cold, and times of communication that match the line of sight between surface, orbiter, and Earth. A spacecraft that flies by Europa profits from this geometry. Close passes can be timed, so a target region sits under the path at the desired hour. If a team wants shadows to stand out, it can aim for a time when the sun is low and the shadows stretch. If a radar instrument needs a clear angle to probe a ridge, planners can choose a path when the ground track and the ridge align. The lock to Jupiter adds another layer. If a team needs to avoid the inward or outward sides for any reason, it can plan passes over the other sides and still return later to the same features under similar conditions. The scale of Europa also shapes how features appear from orbit. A ridge that rises only a few tens of meters can cast a long, clean line under low sun because the horizon is close and the surface is smooth at large scale. A band that runs for hundreds of kilometers can be imaged in full along a limb if the path and timing are chosen well. The brightness of the ice helps imagers by reducing deep shadows under high sun, but challenges them under low sun because contrast rises sharply. A steady, long day gives room to adjust these trade-offs. The fixed inward and outward faces also matter for safe approaches. Jupiter's presence on one side means that some directions in space are busier than others. The side that always looks at Jupiter sees more of the planet's influence. The side that always looks away sees less of it. A careful route that threads between these influences can extend the useful time a spacecraft spends near Europa. The lock simplifies that route planning because the pattern does not rotate under the spacecraft's feet. Even the act of naming features benefits from the simple geometry. With one face always turned in, latitude and longitude grids can be anchored to stable reference points. This avoids slow drifts that would otherwise confuse maps made over many years. A ridge observed under summer light and then again under winter light will line up on the same grid. The grid, the clock, and the path around Jupiter form a backbone for the record of Europa's surface. The brightness of the ice deserves one more note. Bright here means reflective. The term some scientists use is albedo. In plain terms, it is the fraction of sunlight that the surface sends back into space. On Europa, this fraction is high. A high fraction means less energy absorbed and more energy reflected. For anyone designing a small probe or a large lander, that simple fact is central. Solar panels produce less power, surfaces cool quickly, heaters must run longer, cameras must be sensitive to low light reflected from pale ground. All of this starts with the orbit, the spin, and the ice. Long rhythms change how change itself is measured. On many worlds, daily variations repeat quickly. On Europa, they repeat slowly. A frost patch that brightens under midday light will not face that condition again for many hours. A measurement of surface glow in the infrared at midnight will not be repeatable until the next long night. This discourages short experiments and favors longer watches. It also encourages careful notes with precise timing, so later data can be compared with confidence. The small radius and the steady lock also steadies the tides. As Europa moves around Jupiter, the pull raises and lowers the surface in patterns tied to the fixed inward and outward faces and to the leading and trailing sides. These patterns repeat with the day. Cracks that respond to these slow pulls will open and close in step with the long clock. Teams that want to watch such behavior can choose times when the pulls are strongest or weakest over a chosen site. Again, this is a direct chain from orbit and rotation to a schedule for science. Planning for contact with the surface, even in imagination, flows from these same facts. A person or machine on the ground will live under a sun that takes many hours to rise and set. Jupiter will sit in a nearly fixed spot. The ground will be bright when light reaches it, and very dark when it does not. Communication with a spacecraft overhead will come in windows that match the long day and the curve of the horizon. From these simple items, a plan grows seed by seed. When to take images, when to rest, when to heat, when to cool, when to listen, and when to speak. The distance from the sun often invites a simple but important question. How much light is there to work with? The answer begins with the number already given, about 780 million kilometers. At that range, each square meter on the ground receives only a small share of the sun's output. The bright ice then sends much of it away. There is light enough to see by with good eyes and good senses, but not much more. Choices that would be easy closer to the sun become careful here. Exposure times grow longer, power budgets grow tighter, plans grow more deliberate. Even orbit timing depends on these basics. A craft that dives close to the surface threads through a narrow window where the speed, the altitude, and the angle of light line up. Miss that window, and the lighting will not fit the instrument plan, or the target area will lie in shadow. Hit it, and the pass will deliver layers of data that align well with prior passes. Repeat that process many times, and a whole globe can be mapped with a quality that comes from predictability. The geometry of a tidally locked world provides that predictability. The picture forming here is not dramatic, but it is powerful. It is a picture of a small moon with a bright face, circling a planet under a long, slow day, far from a dim sun. It is a world whose clock is set by its path around Jupiter. That clock tells the sun when to rise, which side sees Jupiter, and which features lie under what light at what hour. It is a world whose scale and brightness ask for careful planning. Once these elements are clear, much else falls into place. The length of a work shift, the timing of a pass, the slope of a shadow, the angle of a radar beam, the window for a temperature check, and the confidence in a second look all trace back to orbit, rotation, and scale. From here, it is natural to think about what this setting does to light and heat on the ground. The long day, the dim sun, and the bright ice combine to create a surface that stays cold and reacts slowly. The lack of thick air above the ice also follows from this distance and this brightness. Those conditions form the next layer of the story and rest directly on the foundation laid by Europa's orbit, rotation, and size. How cold can a place become when sunlight is weak and there is no air to hold heat? On Europa, light falls gently and the ground answers slowly. The sun sits far away, so each beam carries less energy than we feel on Earth. The ice that covers Europa is very bright and sends much of that light back into space. Brightness in this context means high reflectivity. Because the surface reflects so much, the ice absorbs little warmth even when the sun stands high in the sky. At local noon near the equator, temperatures reach about -160 degrees Celsius. Farther toward the poles, the cold deepens and the ground can drop below -200 degrees Celsius. These are not sudden spikes. They are the quiet result of weak sunlight and a surface that refuses to take in much heat. Time on Europa also runs with a slow daily rhythm. One day lasts about 85 hours. Warming and cooling stretch over long periods. Morning does not rush, and the same is true for evening. As light gains strength, the surface temperature rises, but not quickly. The soil is not soil at all. It is hard ice at cryogenic temperatures. After local sunset, there is no blanket of air to trap heat. The ground releases energy to space and cools fast over the next hours. Shadows grow colder than nearby lit areas because nothing carries heat sideways through air. Where the sun does not reach, temperatures fall with little delay. The lack of air above the ice is not a small detail. It is one of the main facts of the surface. There is a very thin layer of oxygen near the ground. It comes from radiation breaking water molecules in the ice. The broken pieces sometimes recombine into oxygen, which then floats close to the surface. The pressure is so low that this layer behaves like a vacuum. Molecules of gas travel long distances without hitting each other. Some fall back to the ground, some stick to ice, and some escape into space. Since the gas is so thin, it cannot carry heat the way air does on a planet with a real atmosphere. It cannot make wind, clouds, rain, or snow. It cannot carry sound. Across the open landscape, no sound can travel because there is nothing to vibrate and carry a wave from place to place. Heat on Europa moves in only a few ways. Sunlight brings energy down. The ice absorbs a small fraction and warms. The warmed surface then sends energy away as invisible heat light, which some people call infrared radiation. Heat also moves by direct contact. If a warm object touches cold ice, heat flows from the warm object into the ice. That is called conduction. Without air, there is no convective heat, which is the kind of heat flow where warm gas or warm liquid moves as a current. This simple set of pathways shapes everything that happens near the surface. A tool that sits on the ground will chill unless it makes its own heat or insulates itself. A camera must balance long exposure times with the reality that targets are dim. A heater that keeps an instrument alive must not melt the ground under it, because melting can undermine footing. All of this comes straight from the basic physics of light and heat in a vacuum. Because the day is long, the thermal cycle has room to unfold step by step. In early morning, the sun's rays strike the ice at a low angle. Shadows stretch long and the cold remains deep. As the sun climbs, the light strengthens. Near local noon at the equator, the ground reaches its warmest state, which is still very cold by human standards. Later, as the sun drops, the ice cools again. There is no late afternoon rush of warm air. There is only the surface slowly losing heat to space. The rate of cooling depends on how bright or dark each patch of ground is, how rough it is, and whether nearby features throw it into shade. Darker bands that absorb a little more light can be slightly warmer than bright frost. Fresh frost can brighten a patch and lower its temperature under the same light. These small differences matter to instruments that read temperature and to planners who choose times for measurements. Shadows on Europa are more than lines. They are zones of deep cold. A narrow crack, a low ridge, or a boulder can cast a chill across meters and keep it in place for hours. Since no air moves heat into these spots, they become islands of lower temperature while the sun shines nearby. This contrast helps in science because thermal cameras can find shapes by the way they heat and cool. It also creates risk because a device that moves from sunlit ground into shadow can face a sudden drop in temperature without warning from wind or other cues. Thermal systems must sense their own state and adjust. The thin oxygen layer is often called an exosphere in scientific talks. We can keep the idea simple. It is a wisp of gas that hugs the surface but does not act like air. Radiation from Jupiter and from the sun hits the ice and knocks water apart. Some of the oxygen hangs around for a while. Some reacts to form other compounds like hydrogen peroxide. At the surface, this oxygen and any other simple gas expand freely. There is no thick fluid to slow them and no clouds to trap them. If the ground releases water vapor from a plume or from a small heated spot, the vapor spreads out and thins quickly. This free expansion is a central constraint and a central opportunity. It reduces the chance of local fog that would block a camera, but it also means that any sample a craft tries to collect will be faint and short-lived unless the tool is in the right place at the right time. Optical conditions on Europa are clear. With almost no gas or dust above the surface, the sky is black even at noon, and the sun is a bright point. Jupiter, when it is visible from a given place, stands as a sharp disk. There is no atmospheric haze to soften edges or to scatter light across the scene. For imaging, this clarity is helpful. Fine details stand out when the sun angle is chosen well. But the weak light and the high reflectivity of the ground demand sensitive detectors. Exposure times grow longer, and motion blur can become an issue for low-flying craft if timing is not precise. The brightness of the ice can also trick sensors if they expect darker ground. Careful calibration keeps measurements honest. The absence of air affects sound and communication in a direct way. Shouts, bangs, and engine noises do not carry from place to place across the open. Any sound exists only inside solids or inside the structure of a lander or a rover. Communication beyond a few meters must rely on radio waves or light signals. For teams working at a distance, this is normal, but it is worth stating clearly. The surface is quiet. Only radiation, charged particles, and tiny impacts from space disturb it in any global way. In that quiet, simple sensors can read the ground without interference from weather, but they must also survive cold, heat loss, and radiation without help from an atmosphere that would otherwise cushion and protect. Frost behavior follows from these rules. Water ice at such low temperatures can hold its shape for long times. At the same time, radiation can break bonds and roughen the topmost layers. In places that sit in constant shadow, frost can collect and stay exceptionally cold. In places that see midday sun, the very top may warm a little and let a few molecules escape. Those molecules travel in long arcs and either fall back or leave the moon. Over time, this gentle exchange can change brightness in subtle ways. Instruments that track reflectivity can notice where frost is fresh and where it has been altered. Those signals, tied to the slow daily cycle, give clues about how active the surface is, even without visible events. Engineering must match these facts. A device on the surface cannot rely on air to carry waste heat away. It must radiate heat into space or conduct it into the ground. If it sends too much heat into the ice, it can create a film of melt that refreezes and locks parts in place. Or it can create a weak layer that leads to tilt. If it radiates too little, it will overheat in its own sealed space. Thermal control becomes a careful balance. Good insulation keeps the cold out during the long night. Radiators sized for weak sunlight carry heat away during the long day. Heaters stay ready to guard against fast cooling when the sun drops and shadows advance. The slow pace of the day makes timing important in a different way than on a fast-spinning world. When a team wants to study how a crack absorbs heat, they can watch one spot through many hours as the sun moves slowly. They can take measurements at low sun angles when shadows reveal surface texture, and again at higher sun angles when brightness is more uniform. Thermal inertia, which describes how slowly a material changes temperature, can be estimated by watching how fast a patch warms and cools over the long day. On Europa, with bright ice and no air, thermal inertia is low at the very top but can be higher a few centimeters down. That means the skin of the surface reacts quickly, while deeper layers change more gradually. This depth-dependent behavior is measurable with the right tools and the right schedule. Even simple movements release gas in a vacuum. A drill, a thruster, or a warm instrument can drive off tiny amounts of trapped volatiles from the ice or from the device itself. In an atmosphere, such releases might mix and linger. On Europa, they spread outward fast and thin. Instruments that sniff gases must consider their own output and subtract it from the measurement. Running blanks and standards helps with this. It is not a matter of distrust. It is a method to keep clean records. The long night is a special challenge. Over many hours without sunlight, the surface becomes very cold, and anything exposed follows. Batteries lose capacity when cold. Lubricants thicken, metals and plastics contract, wires and connectors can change behavior. Designs for Europa must accept this and prepare for it. Materials are chosen for low-temperature performance. Moving parts are minimized or sealed. Electronics are placed in warm enclosures. These choices appear simple, but they emerge directly from the measured temperatures at the equator and at higher latitudes, and from the length of darkness in each cycle. At the poles, the problem is sharper. The sun climbs lower, the day stays colder, and night reaches even deeper cold. Some places may never see direct sunlight for very long. These regions become reservoirs of extreme conditions. They can preserve delicate surface chemistry in a more stable state. They can also pose limits for power systems and mechanisms. A clear map of how temperature changes with time and latitude is more than a chart. It is a guide for where to send instruments, how long they can work, and what they can expect to endure. Light and heat also shape the way the surface looks. Bright ice reflects a lot, but it is not uniform. Thin layers of frost can brighten a place. Darker bands can soak up a little more energy and stand out in thermal images. Pits and ridges cast patterns that move slowly with the sun. Careful imaging over one long day can reveal how these patterns change. That in turn can hint at texture, grain size, and the presence of salts or other impurities that change the way ice handles light and heat. Each of these clues feeds back into how we choose sites for close study. Even without weather, there are small changes in surface brightness and temperature that unfold over time. The weak oxygen layer can pick up energy from radiation and glow faintly at specific colors. Instruments that watch for this glow must account for the slow cycle of day and night and the angle of Jupiter's magnetic field lines. This is a case where light, heat, and space environment overlap. The thinness of the gas makes any such glow faint and localized. Detecting it requires sensitive optics and careful timing. When we think about working on Europa, it helps to picture the surface as a place where heat leaves easily and arrives in small amounts. There is no wind to chill a radiator and no air to warm a cold joint. There is no fog to block a laser and no dust storm to coat a lens. There is also no cushion of air to slow a fall or to carry the sound of a crack underfoot. The environment is simple in some ways and strict in others. It rewards careful energy accounting, careful timing, and careful control of heat. These conditions do not exist in isolation. They interact with other forces in Europa's neighborhood. The same emptiness that lets heat escape and leaves the sky clear also leaves the surface open to fast particles from Jupiter. The same cold that keeps ice hard also makes footing uncertain on frost and on bare ice. Understanding light, heat, and airlessness sets the stage for judging those risks with care and for planning motion on the ground with restraint. What happens to a body and to a machine when invisible particles cross them all day long? Near Europa, Jupiter's magnetic field fills space with charged particles. These particles are mostly fast electrons and ions. An ion is an atom or a molecule that has lost or gained electrons and carries an electric charge. These particles spiral and sweep through the space around Europa and strike the ice and anything that stands on it. The flow does not stop at the edge of the sky because there is almost no air to slow or block it. In that open environment, radiation is not an occasional event. It is a steady presence that shapes what is safe and what is possible. Exposure on the ground is not uniform. Some places receive more, some less. Near the equator, the dose can reach several sieverts per day. A sievert is a unit used to estimate how radiation affects living tissue. A dose of several sieverts in a single day is far beyond what an unprotected person can tolerate. It is also high enough to damage many kinds of electronics over time. The side of Europa that trails along the orbit, which is the side that faces backward as the Moon moves around Jupiter, tends to receive more charged particles. The pattern is linked to the way particles move with Jupiter's rotation and magnetic field. Some regions see lower dose because of field geometry and because Europa itself blocks part of the flow. None of these regions is free of radiation. They are simply less harsh. Radiation affects living cells in several ways. Fast particles can break molecules apart. They can disrupt the way a cell copies its instructions. They can make chemical changes that the cell cannot repair. For any mission that involves people, this environment sets a firm limit. Time on the surface would have to be very short, and shielding would have to be very heavy. For robotic missions, the concern is different but just as real. Electronics can suffer from two kinds of effects. The first grows over time as devices absorb energy and materials change. The second happens in a moment when a single particle strikes a sensitive spot and forces a wrong value in a circuit or a memory cell. This second kind can flip a bit in memory, reset a processor, or make a sensor report a false value. Good design can catch many of these events, but it cannot ignore them. Jargon often enters here, so it helps to keep terms plain. When people talk about total dose, they mean the amount of energy a device has absorbed over its life. When they talk about single event errors, they mean sudden glitches from a single particle strike. Both happen near Europa. Both must be handled. Engineers use parts that tolerate high dose. They add error checking and correction to memory. They include extra circuits that can take over if one fails. They plan for resets that do not destroy data. These measures do not make radiation go away. They give systems a way to continue to work in spite of it. Another piece of the risk picture comes from motion on the ground. Europa's surface gravity is about 1.315 meters per second squared. That value shapes every step and every wheel turn. When someone or something pushes off the ground, the path through the air will be longer and slower than on a world with stronger gravity. Stopping takes longer. Steering must be gentle. A small slip can send a body or a rover sliding across hard ice. There is no air to help slow the slide. Traction is poor on frost and poor on exposed ice. This is not a guess. It is a direct result of very cold, very hard ice that does not deform to provide grip. Falls are not loud on Europa because there is no air to carry sound, but they can be severe. Hard ice does not cushion. A stumble on a slope or at the edge of a crack can send a device into a long glide. A human in a protective suit would need spikes and tethers. A rover would need wheels or feet that can bite into ice. The risk is not only slipping, it is also inability to stop quickly. Motion planning must allow for long braking distances and must avoid sudden moves. It is a style of movement that favors patience. Radiation and motion do not act alone. They interact with the cold, the brightness, and the vacuum described earlier. In the cold, many materials become stiff and less forgiving. Joints can seize. Lubricants can thicken or stop flowing. Plastics can crack. When fast particles hit these materials, they can add stress by breaking molecular bonds. Electronics grow more vulnerable as dose accumulates. Sensors can drift. Wires can change resistance. The vacuum removes heat by radiation only, so warm parts cool quickly in shadows, and cold parts can stay cold for a long time. A machine that is trying to keep its footing cannot easily use melting to gain grip because meltwater would refreeze and change the contact in unpredictable ways. Planning around radiation starts with knowledge. Instruments can count particles and measure dose in real time. These readings can be tied to location on the ground and to local time in the long day. Over many orbits, a map of dose rates can be built. Such a map helps to choose safer corridors and safer places to pause. In practice, there will still be trade-offs. The most interesting science sites may lie in regions with higher dose. The lowest dose spots may be far from good landing areas. This is why mission designs often rely on short, targeted operations with clear start and end times. Shielding around key electronics can be thickest. Sensors that must face the sky can be more exposed, and their life can be managed. Shielding is a simple word, but it is a complex choice. Materials that block charged particles add mass. Every kilogram added to a spacecraft changes its fuel needs and its path. The art is to place mass where it matters most, to leave low-risk parts lighter, and to route cables and connectors in ways that reduce direct paths for particles. Some designs bury sensitive electronics deep inside the body of the craft. Others wrap boxes in layers that slow and spread out the particle energy. For memory, designers add circuits that check data as it is stored and retrieved, and that can detect and correct a flipped bit. For processors, designers include watchdog timers that restart a system when it stops responding. Radiation also shapes how measurements are taken. A camera image can show speckles when a particle crosses the detector during an exposure. A mass spectrometer can pick up false counts when a particle strikes inside its chamber. A magnetometer can see tiny jumps. To keep confidence high, teams collect multiple frames, repeat scans, and compare overlapping data. They also include internal references. These are targets inside the instrument that should never change. If a reading changes on the internal target, it is a sign that the instrument itself has drifted and needs correction. Motion planning benefits from similar discipline. Paths are chosen for gentle slopes and stable surfaces. Sharp edges, narrow cracks, and fields of large blocks are avoided when possible. When not possible, crossings are made with anchors, with tethers, and with slow, deliberate steps. Testing on Earth helps, but conditions are not the same. Real traction on hard ice at very low temperature in near vacuum is hard to reproduce. This is where sensor feedback is key. A rover can watch it slip, measure wheels spin against movement, and adjust on the fly. A human would rely on force feedback through tools and on clear visual cues. Cameras and depth sensors must handle the bright, reflective surface without glare and without deep shadow loss. The long day makes a difference here as well. Motion can be scheduled during long periods of steady light, so that shadows do not surprise the system. Rest can be scheduled when the sun is low and shadows grow long across slopes and ridges. The timing must also account for radiation dose. If a site lies on the trailing side and dose is higher there, a visit can be kept short, with longer stays planned on the leading side or on locally sheltered spots. These patterns emerge from the fixed geometry of a tidally locked world and from the measured environment around it. Another quiet risk comes from static charging. In a vacuum, surfaces can build up electric charge under radiation. This charge can discharge suddenly. Such discharges can upset electronics and can startle sensors. Designs include paths for charge to leak away slowly, grounding straps between parts, and coatings that reduce buildup. Testing these features under strong radiation and cold helps verify that the measures work. It is natural to ask whether the ground itself provides any shelter from radiation. If a device sits in a low spot or behind a ridge, the local mass of ice can block some particles arriving from those directions. Since particles come from many directions, and since some follow complex paths along magnetic field lines, shelter is partial. Cavities and overhangs, if present, would provide more mass overhead and more protection. Finding such places is a mapping task and a motion task. It is also a balance with other risks, because overhangs can be unstable and cavities can have thin roofs. The combination of low gravity, poor traction, and high radiation compresses time and stretches space. A move of a few tens of meters across easy ground could be simple. A move of the same length across fractured terrain with slopes and blocks could take many hours and carry higher risk. A pause under high dose eats into the total exposure budget. A slip that forces a recovery burns time and uses up power that must be replaced during a long night. The result is an operational style that favors modest goals each day, firm turn-back rules, and constant awareness of the environment. Behind all these operational notes lies the surface itself. The ground is not smooth. It is marked by long, dark lines, paired ridges with central grooves, wide bands where ice seems to have opened and refilled, fields of shallow pits, and jumbled zones where blocks several kilometers across have moved and refrozen. Each of these features affects motion in its own way. A double ridge can be a barrier with a trough that traps wheels or feet. A band can be rough in the center and smoother at the edges. A chaos area can present broken plates and hidden gaps. The patterns are not random. They follow stress in the ice and record events in the crust. That record is both a hazard map and a science map. Radiation adds a layer to that map. The trailing side, which sees higher particle flux, tends to host more altered surface chemistry. Salts may darken under radiation. Ice may become rougher at the very top as molecules are split and moved around. These changes can reduce reflectivity and change how heat is absorbed and emitted. A darker patch can be slightly warmer at noon and may be slightly softer under a spike. This does not remove risk. It changes it. Sensors that watch for shifts in brightness and temperature can pick out such areas and adjust plans. It helps to imagine a simple task. A rover wants to cross a narrow fracture, take a sample on the far side, and return. First, it checks radiation dose so far that day and the time remaining before reaching a limit. It checks that temperatures are within range and that heaters can sustain if a long pause occurs in shadow. It images the fracture at low sun to gauge depth from the darkness inside, and again at higher sun to gauge width. It tests the ice near the edge with a small push to see if the crust crumbles. It sets anchors, one on each side if possible. It moves across with its weight distributed low and wide. It takes the sample with a tool that minimizes heating. It seals the sample to prevent vapor loss in vacuum. It returns along the same anchors. At each step, it logs sensor readings because radiation can play tricks on data. This scenario sounds careful because caution is the path to lasting work in this environment. Humans are unlikely to stand on Europa for long under such dose rates, but the planning logic is the same. Set limits, move slowly, choose stable ground, and design every system to fail safe. The cold and the vacuum remove the cushion that air and warmth provide elsewhere. Radiation removes time. Gravity removes quick stops. These realities become steady guides rather than reasons to avoid the place. They point to tools that have spikes and screws for grip, to software that watches for slips and recovers, to electronics that survive errors and keep going, and to maps that show not only shapes but also doses. As work continues from orbit and during flybys, better knowledge of dose patterns and surface texture will refine these plans. Ice-penetrating radar can show where layers are intact and where they are broken. High-resolution images can map ridges, bands, and chaos in detail. Magnetometers can hint at currents below that may relate to surface features. Mass spectrometers can sample the faint gases above the surface and link chemistry to terrain. Each new layer of information makes risk assessments more precise and opens paths that were not obvious before. In the end, radiation and motion risks are not a separate chapter from Europa's nature. They are consequences of the same facts that define the world. A bright ice shell far from the sun, a lock to a giant planet, a thin wisp of oxygen at the surface, and long tides that flex the crust. The ground itself carries the record of that flexing and that motion. Dark lines, ridges, bands, pits, and jumbled fields are the features that a rover or a person must cross, and also the features that tell the story of the moon. Understanding those patterns is the first step in choosing a safe line on the ice and in reading the events that shaped it. What do the lines on Europa's ice tell us about the world that made them? From a distance, Europa looks smooth and bright. Up close, the surface is marked by a dense web of dark lines that run for hundreds of kilometers, bend, fork, and cross. Some of these lines stand as narrow ridges with a trough along the top. Others are flatter bands that are wider and darker than the land around them. Between and across these features lie fields of shallow pits and broad regions where the crust looks broken and jumbled, with large blocks shifted from their original places and set again into new positions. The ground is not simple, it carries a busy record. The long lines vary in form and tone. Some are crisp, with sharp edges and little change in width along their path. They cut across bright frost and older ground cleanly, which shows they formed after those surfaces were laid down. Others are diffuse and uneven, with borders that fade into the surrounding terrain. Many run straight for a while, then kink or curve, then straighten again. Where two lines cross, one sometimes preserves its shape with little interruption, the other breaks and continues on the far side. These small clues help build a timeline. The continuous line is younger at that crossing. The broken one is older there. The height along many lines is modest, yet real. Ridges can reach up to tens of meters above the flats. The central troughs can drop a few meters below the ridge tops. Slopes can be gentle on one side and steeper on the other. The relief matters. It guides how shadows fall during the long day and how a rover or a lander foot would grip or slide. The ridges are often paired, with the trough down the center between them. The symmetry is not perfect, but it is common. The pattern points to a process that lifts ice from below or pushes outward from within a shallow layer. The details of that process depend on how ice behaves when it is cold and stressed, and on what materials, like salts, are mixed into it. Wide bands tell another part of the story. These are broad, dark stripes that can stretch for hundreds of kilometers, wider than the narrow ridges. Their edges can be straight and parallel for long distances. Inside, they show textures that suggest the surface opened and new ice filled in the gap. In some places, small ridges and cracks inside a band run parallel to its edges, like growth lines. The darkness of many bands may come from material brought up from below that contains salts or other compounds. It may also come from ice with a different grain size or structure that reflects light less efficiently. The exact reason can vary from band to band. Fields of shallow pits dot some regions. Each pit is usually round or slightly oval and shallow with gentle edges. They often cluster in groups and can align along faint lines or form patterns that hint at underlying structure. Their sizes vary, but many are a few tens to a few hundreds of meters across. The origin of these pits is not yet settled. They could be places where near-surface ice lost molecules to space faster than the ground around it. They could be small collapses where a thin crust gave way over a cavity. They could also be spots where warm pockets in the ice were present for a time and changed the texture. The key point is that pits often occur with other active features, which suggests a link to processes that affect the near-surface layers. The most striking terrains are the jumbled regions that many researchers call chaos. In these areas, the crust looks shattered and reset. Blocks several kilometers across have shifted, rotated, and settled into a matrix of smaller fragments and refrozen material. The edges of the large blocks can be traced and matched like pieces that once fit together. Their rotations are not random. They show that the crust broke along curving lines and that the blocks moved a short distance before stopping. The material between the blocks appears to have flowed or been emplaced as slush and then refrozen. The sizes of blocks, the widths of gaps, and the distribution of dark material hold clues about how deep the disruption reached and how much heat or liquid was present when it happened. Narrow fractures are common and can be very young. They slice through bright frost and older deposits with little erosion of their sides. Many are only a few meters across, but they can run for many kilometers. Their darkness suggests that fresher material or shadows in the crack contribute to the color. These fractures can link larger features. They can also form nets that divide the surface into plates with sizes from a few meters to many kilometers. The nets do not repeat perfectly. They shift direction across the surface, which shows that the forces that made them change from place to place and over time. All these shapes are easier to see and measure because the sky above Europa is clear. With almost no air, there is no haze. Shadows fall sharply when the sun is low. Brightness changes are tied to the ground itself, not to clouds or dust. The long day gives time to watch how light and shadow move slowly across ridges and pits. When the sun is near local noon, wide bands and chaos patches reveal their textures without deep shadows hiding them. When the sun is low, ridge height and pit depth stand out as lines of light and darkness. This steady rhythm of light supports deliberate mapping. Texture and color are not only visual impressions, they connect to composition and to temperature. Darker lines and bands tend to absorb a bit more light and can be slightly warmer near midday than bright frost around them. At night, everything cools deeply, but differences in the speed of cooling can show where the surface structure differs. Thermal data that record how fast a place warms and cools, tied to images that show its form, allow estimates of grain size and porosity in the topmost layer. In simple terms, grain size is the size of crystals in the ice. Porosity is how many empty spaces exist between grains. Coarser grains and fewer spaces tend to change temperature more slowly. Finer grains with more spaces change faster. These properties vary across ridges, bands, pits, and chaos. Orientation matters too. Many long lines share preferred directions. Sets of lines can run roughly parallel over large areas. Elsewhere, they curve around or radiate from a point. The repeat of directions hints at stress fields in the ice shell. Stress fields are patterns of push and pull that act on the crust. They arise from tides raised by Jupiter, from the shape of Europa, and from changes in the shell over time. Where the stress is strongest in tension, cracks open. Where it is strongest in compression, old gaps may close or layers may buckle. The directions along which lines run and the ways they cut across each other give a record of how these stresses changed. At times, the surface seems to have spread apart gently along a band while new material rose to fill the gap. At other times, the ground appears to have failed over a region, breaking into plates and settling into a softer base. Both styles are present. Both require energy and a way to make ice move or melt a little. One way is through heat from within, another is through salt mixed into the ice. Salt lowers the freezing point of water. A salty patch in the shell can stay soft at a lower temperature than pure ice. If such a patch is shallow, it can feed the growth of a ridge as it refreezes and pushes the sides up. If such a patch is deeper and broader, it may weaken a larger region so that it breaks into blocks. The edges of chaos areas vary. Some end abruptly against intact terrain with a clear line between broken and unbroken ground. Others grade into fields of pits or into bands. This variety suggests that chaos can begin in different ways. Local warming from below could soften a region until it fails. Stress from above could break a region where the shell is thin or where older lines have weakened it. The presence of salts could focus the effect by keeping a zone softer than its surroundings. The balance among these factors likely shifts across the globe. For anyone planning a landing, this landscape is both a guide and a warning. Smooth plains between major features may offer the safest touch points, but they are often narrow. The tops of ridges may be too narrow and too steep for stable legs. The troughs can trap. Band interiors may hold rough textures and small relief that threaten wheels. Chaos fields can hide thin crusts over voids between blocks. Pits can be shallow, but their edges can crumble. The key is to use high-resolution images to spot slopes, block sizes, and shadow patterns, and to pair that view with thermal maps that show stability over the long day. Even then, caution remains wise, because what looks smooth from above can hold surprises at the scale of a meter. Imaging alone does not tell the whole story. To know what lies below, radar that can penetrate ice helps. Reflections inside the shell can reveal layers, buried ridges, and zones where the signal is scattered by rough ice. A zone of many scatterers below a chaos region could indicate a volume of broken ice. A strong, flat reflection under a band could indicate a coherent layer that continues beneath it. These readings tie surface form to internal structure. They also guide interpretations of how a feature formed. A ridge above a zone that holds a thin, lens-shaped layer of different material suggests freezing of a shallow pocket. A chaos region without strong internal reflections could point to more uniform refreezing. Color data add another layer. Spectral measurements can identify salts in some places. Sodium chloride and magnesium sulfate are two candidates that often appear in studies. If a band or a chaos area shows signs of such salts, it strengthens the case that material from below reached the surface there. That does not mean liquid stands open at the surface. It means that briny ice or water once moved within the shell and carried dissolved material upward. In 2023, a map of carbon dioxide in a region named Terra Regio added weight to this view. The presence of carbon-bearing material at the surface in a pattern tied to a geologic unit suggests exchange between interior and surface. That is one reason these patterns are so valuable. They are not only shapes, they are pathways and records of exchange. Relative age can be read from cross-cutting and from how fresh features look. Lines that cut across many other features are often younger. Surfaces with bright frost and sharp edges are often younger. Darker, rougher surfaces that have been cut by many later lines are often older. Building a map of relative age helps trace how stress rotated and how the shell responded over time. It also helps target sites that record recent events, where any chemical signals might be less altered by radiation. The trailing hemisphere, which sees higher particle flux, often shows more processed surfaces. The leading hemisphere may hold fresher frost in some regions. These broad notes must be filled in with detailed mapping, but they set a frame. On Europa, there is no weather to erase lines or to blur edges quickly. Change comes from inside the shell, from radiation darkening the top few millimeters, and from small impacts. This means that the surface features can last a long time. It also means that when change does occur, it stands out. A new fracture on bright frost, a fresh band across older tracks, or a subtle shift in a chaos block's edge can be detected if we have good images before and after. That is why repeated passes with similar lighting and angles are so valuable. They allow honest checks for change without confusion from shifting shadows or different sun angles. Hazards and science go together in this setting. The same ridges that threaten a wheel also record the pressure of freezing pockets. The same pits that can break a thin crust also trace the locations of weak layers. The same chaos that blocks a path carries evidence of uplift, softening, and refreezing. To move safely, we must read these signs. To learn well, we must visit them with care. Anchors that grip hard ice, feet that spread load, and schedules that avoid deep shadow near steep relief are practical lessons drawn straight from the terrain. The picture that forms from these patterns is one of active ice, even though the surface is very cold. The activity is not in the form of flowing rivers or gusting winds. It is in slow spreads, sudden breaks, and local upheavals driven by forces within the shell. The source of those forces is not a mystery. Jupiter pulls on Europa and flexes it. The shell warms and cools with a long day. Salts change the freezing point locally. Pockets of liquid can form, move, and refreeze. Each shape we see is a response to these drivers. To understand why a ridge rises or a band widens, or why a chaos block turns and settles, it helps to know how ice at deep cold responds to being pulled, pushed, and warmed. Sometimes it breaks like brittle glass under a sudden strain. Sometimes it deforms slowly under a steady load. Sometimes a small amount of melt or brine changes everything by greasing a zone or by expanding when it freezes. The surface features are the trace of this behavior written into the ground. Reading that trace well depends on knowing the rules that ice follows under stress. How does ice break, bend, and heal on a world this cold? Europa's surface carries long lines, paired ridges, wide bands, pits, and jumbled blocks. These shapes are the trace left by ice under stress. To understand the record and to plan any careful work on the ground, it helps to start with a simple rule. At the temperatures measured on Europa, ice is very hard. Under a sudden push, it tends to crack. Under a slow squeeze, it can change shape without snapping. When stress rises fast, the surface fails in a brittle way and a fracture opens. When stress rises slowly and stays below a limit, deeper ice can creep. Creep is a slow, steady change of shape that continues as long as the load remains. Which mode happens depends on temperature, on how fast the force rises, and on how long it lasts. Cooling and warming add their own rhythm to this behavior. When ice cools, it shrinks a little. When it warms, it expands a little. On Europa, the daily cycle is long, and the change in temperature between day and night is large near the skin of the surface. Shrinkage during the long night puts the top layer in tension. Tension is a pulling stress that tries to pull a material apart. If the pull is strong enough, small flaws at the surface can grow into cracks. As morning comes and the skin warms, the pull relaxes. The crack may close a little, but it does not always heal. The next cycle can open it farther. Edges and corners focus stress, so lines tend to start and grow at places where shapes and materials change. Jupiter adds a steady, repeating force from the outside. Europa's path around the planet is slightly oval, and its spin is locked. The pull on the near side and the far side changes as Europa moves. This flexes the shell on a cycle that repeats with each day on Europa. During one part of the cycle, certain regions are pulled apart. During another part, those same regions are pushed together. The pattern slides slowly across the surface in step with the orbit. Existing fractures respond to this pull and push. Many open a little during one phase and close a little during the opposite phase. Over many cycles, this breathing action can grow a crack longer and can turn a short break into a structure that crosses a large area. The thickness of the shell and the texture of the ice control how big these effects can be. Where the ice is thicker, the surface can carry stress over longer distances, and the crust may bend rather than snap for a given force. Where the ice is thinner, stress can break through more easily and cracks can propagate faster. Grain size matters too. Ice is made of crystals. Where crystals are small and their boundaries are many, the material can change shape slowly under load more easily over long times. Where crystals are large, it takes more stress to move them past each other. Temperature also increases with depth, so deep ice is warmer and more able to creep than the skin at the top. The top few meters are the most brittle. Deeper layers can accommodate stress more gently. Salt mixed into the ice changes everything in a quiet way. Salt lowers the freezing point of water. In zones where salt is present, small pockets of salty water can remain liquid at temperatures where pure water would be solid. These pockets can exist at shallow depths, possibly only a few hundreds of meters below the surface. When stress opens space, liquid can move into that space. When stress relaxes, the liquid can refreeze. Freezing releases heat and also expands the volume of the liquid. That expansion pushes on the walls around it. If this refreezing happens in a zone aligned with a fracture, the pressure can lift the sides and build a pair of ridges with a trough between them. This is a plausible path for the formation of many double ridges seen on Europa. Bands speak to a different kind of stress. When the shell is pulled apart over a wide region, a gap can open and be filled by new material from below. If the supply is warm, slush, or soft ice, it can spread laterally as it refreezes. The edges of the band remain clear, and inside the band, lineations can form that parallel the boundaries. Darker tones in many bands suggest that this new material carries salts or other compounds that alter reflectivity. The mechanics are consistent with slow extension over long times, punctuated by opening events that add width in steps. Chaos terrains are evidence of local failure in the crust. A region can weaken if it is warmed from below, if it contains a larger amount of salt, or if repeated stress breaks it along many lines. When weakness reaches a threshold, the upper layer can detach in blocks and settle into a softer base. The blocks rotate and move a short distance. The gaps between them fill with slush that later refreezes. The edges of blocks can be traced and matched, showing that the motion was limited. The distribution of block sizes and the look of the refrozen matrix point to the depth and intensity of the disruption. This is not a story of fluid water flooding the surface freely. It is a story of local softening and breakup within the shell. The open and close cycle of cracks is not only an idea on paper, it leaves signs. Sharp fractures that cut bright frost and older ground are often aligned with the directions of present-day pulling stress. Lines that have been squeezed show evidence of compression, such as raised margins or small buckles. In some places, a ridge will be younger along one stretch and older along another, telling us that local stress rotated over time. With careful mapping and timing, these patterns can be linked to the long clock of the orbit. The cycle repeats, and the ground responds in phase with it. This behavior sets design rules for tools. Anchors that grip the surface must handle brittle failure at the very top and slow creep at depth. A screw that bites too hard can crack the ice it sits in. A foot that spreads load can avoid that. A tether that holds tension must account for slow stretch in its anchor points if the ground beneath is creeping. Instruments that send signals into the ice must account for crack opening and closing that change the path of waves or radar pulses. Measurements repeated at different phases of the cycle can reveal these subtle changes and help map the three-dimensional structure of the shell. Timing work to the stress cycle is a practical step. If a task requires crossing a narrow fracture, a safer window is when compression is expected locally and the gap is smallest. If a task seeks to sample fresh material from within a ridge, a better window is when tension is present and small openings might vent trapped gases. To use timing well, the pattern of stress at the surface must be forecast. Models of Europa's flexing tie the orbit, the orientation on the surface, and the known properties of the shell into such forecasts. They are tested against images, against thermal maps, and against radar that can see shallow voids and lenses. Under slow, steady load, deep ice flows over long times. This flow can fold layers. It can bend the crust gently. It can close old voids. It can also drag briny pockets sideways or upward. Where the shell has layers of different grain size or different salt content, each layer responds with its own pace. A stiff layer over a soft layer can decouple motion, focusing stress at their boundary. The long lines we see on the surface can mark such boundaries or mark places where stress focused repeatedly because of them. Laboratory work supports this picture. Samples of ice cooled to temperatures near those on Europa show brittle behavior under fast loads and ductile behavior under slow loads. Additions of salts such as magnesium sulfate and sodium chloride lower the temperature at which ice softens and increase the amount of deformation before brittle failure. Repeated small loads can grow micro cracks in brittle ice, which then link up into larger fractures. At the same time, under steady load, grains can rotate and boundaries can move, allowing slow shape change. These results guide models of how an icy shell with mixed composition behaves on a moon with a long day and a steady flex from a nearby giant planet. The surface record shows that both sudden events and gradual processes operate. A single opening event can lay down a narrow line that runs straight for many kilometers. A series of such events can widen a band step by step. A gradual drift of stress can bend lines and change their direction. A broad period of weakening can produce a chaos field, and later, slow cooling can lock it back into place. The presence of salts steers where these events happen because salty zones stay softer at low temperatures, and because refreezing brines release heat and expand. Both effects promote uplift and movement where stress allows it. Depth matters when we think about where liquid can exist and where it cannot. The very top meters are exposed to the vacuum and to extreme cold. Liquid there would not persist. A little deeper, temperatures are still very low, but pressure is slightly higher and the day-night swing is reduced. In those layers, brine can remain behind tiny cracks and pores, especially if salt content is high. Deeper still, at many hundreds of meters to kilometers, more uniform conditions allow larger lenses of brine to stabilize in weak zones. These lenses can feed ridges or bands when stress opens pathways. When they refreeze, they leave traces in the internal structure that radar can detect as changes in reflection. As ice cools and warms with the long day, and as it flexes with the orbital tide, it stores and releases stress. This storage and release can be thought of as a sobering rhythm that runs in the background of every surface process. It slows sometimes and speeds sometimes, but it never vanishes. Over very long times, this rhythm also moves heat through the shell. Friction from slow movement generates a little heat. Refreezing releases heat. Opening and closing change how easily heat flows in and out of cracks. These small effects join with a larger source of heat that comes from the whole moon being flexed by Jupiter on a constant schedule. Together, they keep parts of the shell active even in deep cold. For safety and for science, this understanding shapes choices. A landing site away from chaos and away from the sharpest ridges reduces the odds of sudden ground movement. A traverse that crosses bands at right angles rather than along them reduces long exposure to rough textures. Sampling that targets the edges of features may capture material brought up from depth while avoiding the steepest slopes. Scheduling measurements of ridge profiles at different hours over many days can reveal whether parts of a ridge rise and fall by small amounts. Subtle changes at the level of centimeters would be impressive in such a harsh place, and careful instruments can reach that sensitivity if they are protected from radiation and extreme cold. The behavior of ice under stress also tells us something about the structure we cannot see directly. A shell that opens, spreads, and breaks in the ways observed must be thick enough to support the shapes we map, yet thin enough to flex and respond to tides on a daily cycle. Many models that match these patterns point to an ice shell that is on the order of 10 to 30 kilometers thick. Beneath that shell, evidence from magnetic readings points to a layer of conductive liquid. If a deep liquid layer exists, it decouples the shell from the rocky interior. That decoupling allows the shell to shift and bend more than it could if the entire body were solid. The surface record of stress and motion supports this picture even before we discuss the separate magnetic evidence. Where water meets rock at the base of that liquid layer, chemical reactions can release energy. This energy does not depend on sunlight. It depends on the minerals in the rock, the dissolved salts in the water, and the temperature and pressure in the deep interior. The mechanics of the ice shell matter here because they set the rate at which materials from the surface move downward and materials from below move upward. Cracks, bands, and ridges are not only shapes, they are potential paths for oxidants made at the surface to enter the shell and for brines with reduced compounds to rise. When these substances meet, they can drive chemical gradients that living chemistry could use, if any exists. This chain from stress to shape to exchange is practical. Instruments that sniff the thin gas above the surface can look for small bursts of molecules near features that open and close. Cameras can look for fresh frost along new lines. Radar can watch for changes in shallow lenses that would be expected if the cycle of stress were moving liquid around. Magnetometers can detect small changes in the induced magnetic field if brine flows shift in volume. Each of these observations ties mechanics to chemistry and to the deep structure of the shell. The cold and the vacuum do not erase this activity, they set the rules. The rules say that sudden pushes break ice. Slow pushes can bend it. Cooling opens cracks. Warming can close them a little, but not always heal them. Salts keep some water liquid where pure water would freeze. Repeated flexing makes small changes add up. With these rules in mind, the surface patterns become readable. A ridge is not only a ridge, it is a record of pressure from refreezing brine. A band is not only a stripe, it is a record of extension and of new ice added from below. A chaos field is not only a jumble, it is a record of a region that softened and failed, then refroze. Reading the ground this way opens the door to deeper questions. If the shell moves and changes, where does the energy come from to keep it active? If liquid exists beneath the shell, how thick is that layer and how does it carry heat and salt? If the rock below reacts with water, what amounts of energy and what products result? The behavior of the ice under stress points toward an interior with both liquid water and steady sources of heat. To understand that interior with care, we turn to the signals of a hidden ocean and the energy that keeps it from freezing. How do we know there is an ocean we cannot see? Clues come from a signal in the magnetic field around Europa. A spacecraft named Galileo flew past Europa several times and carried an instrument called a magnetometer. A magnetometer measures the strength and direction of magnetic fields. Jupiter has a strong magnetic field that changes with time at Europa's location. When a changing magnetic field passes through a material that conducts electricity, electric currents form inside that material. Those currents create their own magnetic field. This process is called induction. The pattern that Galileo measured near Europa matches what we expect if a global layer of salty liquid lies under the ice. Pure water does not conduct well, but water with dissolved salts does. The data show a response in both strength and timing that fits a conductive shell under the crust. Models that reproduce this induced signal point to an ice shell over a liquid layer. The estimates for the ice thickness fall near a range of about 10 to 30 kilometers. The liquid layer below that could be tens to more than 100 kilometers deep. The total amount of water in such a layer would be on the order of a few billion cubic kilometers. These values are not measured directly. They are the range of numbers that caused the calculated magnetic response to match the observed one. There is uncertainty because the true salt content, temperature, and exact structure of the ocean and ice affect how well they conduct. Pressure in the deep interior is intense. Pressure is measured in units called bars. A bar is a standard unit for how much force is applied on an area. At the seafloor under a liquid layer tends to more than 100 kilometers deep, pressure could reach thousands of bars. Under such pressure, water stays liquid if it is warm enough and if salts are present. Ice that forms under high pressure can take forms that differ from the ice we see at the surface. Those forms are solid and dense and can act as part of the lower shell. The arrangement of these layers depends on temperature and on the amount of salt in the water. Inside Europa, beneath the ocean, the rock is made mostly of silicate minerals. Silicate minerals are rocks built mainly from silicon and oxygen atoms. Deeper still, a core rich in iron likely sits at the center. This layered interior is a common outcome when a small world forms and cools. Heavy materials sink toward the center. Lighter materials remain near the outside. In Europa's case, ice and water make up the outside layers. Rock forms the middle. Iron forms the center. Water touching rock is not a passive contact. When hot water touches certain rocks, chemical reactions can occur. These reactions can release energy and produce dissolved substances such as hydrogen. Hydrogen is a small molecule that can serve as a fuel for simple chemical systems. If such reactions occur at Europa's seafloor, they would not need sunlight. They would need only water, rock, and heat. The extent of this activity depends on temperature in the rock, the kinds of minerals present, and how much fresh water reaches the reaction zones. Where does the heat come from to keep liquid water present under so much cold and pressure? One major source is gravitational flexing. Europa's orbit around Jupiter is not a perfect circle. It is slightly oval. This shape does not smooth out with time because Europa's motion is held in a repeating pattern with two other moons named Io and Ganymede. This repeating pattern is called a resonance. A resonance is a stable rhythm where orbital periods keep a fixed relationship. Because of this rhythm, Europa's distance from Jupiter changes slightly during each orbit. The pull on Europa changes with distance. The changing pull flexes Europa's body. Flexing causes internal friction, and friction produces heat. The total power from this internal heating is estimated to fall between about 1 trillion and 10 trillion watts. That is a wide range, but even the lower end is large on the scale of a moon. This energy does not all move in the same way. Some of it warms the ice shell. Some of it warms the rocky interior. The split depends on how the ice and the rock respond to repeated stress. If the ice is softer at certain depths because of salt or temperature, more heat can be made there. If the rock is more deformable at certain places, more heat can be made there. The pattern can change over long times, which would affect how thick the ice shell becomes and how the ocean moves. In the ice shell, heat can move upward by conduction, which is transfer through direct contact between molecules, and by slow movement of the ice when it creeps under load. If heat from below is strong enough, parts of the shell can become warm and soft enough to start convecting. Convection is a slow overturn where warm material rises and cool material sinks. This process can carry heat more efficiently than conduction alone. If convection occurs in the shell, it would reduce the thickness of the rigid, brittle lid at the top. A thinner, brittle lid would be more prone to form the cracks and bands that we see at the surface. If convection does not occur, the shell would need to move heat only by conduction, and the brittle lid would be thicker. Both states may occur at different places or at different times. In the rocky interior, heat from flexing and heat from the natural decay of radioactive elements both play roles. The decay of radioactive elements in rock produces steady heat over very long times. This heat adds to tidal heat and helps keep water warm where it meets rock. If parts of the rock are hot enough, Water percolating through cracks can drive the reactions that release hydrogen and other dissolved chemicals. These are basic, well-studied reactions that do not require sunlight. They require only certain minerals, water, and heat. The ocean itself is not likely to be uniform. Salinity, temperature, and pressure vary with depth and from place to place. Water that receives more heat from below rises slowly. Water that loses heat to the ice above sinks slowly. Differences in salt content change density and can cause layers to form. If parts of the ocean carry more salts from the seafloor, they may be denser. If parts of the ocean lose salt to forming ice at the base of the shell, they may be less dense. These contrasts can drive currents. Even slow currents matter because they carry heat and dissolved substances across large distances over long times. The ocean also interacts with the ice from below. When ocean water freezes onto the base of the shell, it leaves most of its salts behind. This process pushes salts back into the liquid and can enrich the ocean near the freezing front. When ice at the base melts, it takes heat from the ocean to do so and cools the nearby liquid. If the shell is thin in one region and thicker in another, the patterns of freezing and melting vary across the globe. This uneven pattern adds complexity to ocean motion and to the distribution of salts. Induction measurements do more than hint at liquid. They can, with enough passes, set limits on the ocean's salinity and thickness. The timing of the induced response compared to the changing field from Jupiter depends on how easily electric currents can flow. If currents form easily and quickly, the induced field responds quickly. If currents face resistance, the induced response lags. This difference in timing, when measured well, constrains the combination of thickness and conductivity. Conductivity depends on salt content and temperature. A warmer, saltier ocean conducts better than a colder, fresher one. Future magnetometers can take many readings across different longitudes and latitudes and reduce the range of possible models. Gravity measurements add another window. A spacecraft that flies very close can sense small changes in Europa's gravity as it passes over regions where ice is thicker or thinner. Over many passes, a map of gravity variations can be built. Combined with topography from imaging and with radar that can probe into the ice, these data sets can reveal where the shell bends under loads, where it is thick, and where it may be thin. Such maps do not show liquid directly, but they reveal the framework that the liquid and the ice build together. The presence of a deep ocean also changes how Europa responds to tides. If the shell floats on a liquid layer, it can move more under Jupiter's pull than if the whole body were solid. This extra movement can be measured as slight changes in shape and in the gravitational field. Measurements of this kind have already been made by timing the motion of the spacecraft during flybys. The results are consistent with a decoupled shell. A decoupled shell is one that can slide over liquid rather than being locked to solid rock below. All these threads form a coherent picture. A conductive layer beneath the ice produces a magnetic response that matches a salty ocean. The ice shell thickness that fits the data ranges around 10 to 30 kilometers. The ocean beneath extends tens to more than 100 kilometers. Pressures at the seafloor reach thousands of bars. Rock of silicate minerals lies below the water, and a core rich in iron sites at the center. Jupiter's pull, kept in a steady rhythm by resonances with Io and Ganymede, flexes Europa and produces heat. That heat, together with slow radiogenic heat in the rock, keeps the ocean from freezing solid. There are uncertainties. The exact salt mixture is not known. Sodium chloride and magnesium sulfate are candidates, but their proportions are not fixed by present data. The ocean may be layered, with different salinity at different depths. The thickness of the ice shell likely varies from place to place. Convection in the shell may be active in some regions and not in others. Heat production in the rock may be uneven if the rock's composition varies. These open points motivate careful measurements and cautious interpretation. Even with these uncertainties, the implications are clear. A large volume of liquid water exists in contact with rock, supplied with steady heat. Chemical gradients can form where reduced materials from the seafloor mix with oxidants that reach the ocean from above. Oxidants at the surface form when radiation breaks water molecules in the ice and leaves behind oxygen and hydrogen peroxide. If any of those oxidants can move downward through cracks or by slow overturning of the ice shell, they can meet reduced substances that rise from the rock. Where they meet, energy can be released through simple reactions. The surface record discussed earlier fits into this framework. Bands show where new material likely flowed and refroze as the shell stretched. Double ridges point to freezing of shallow pocket liquids that pushed the ice up. Chaos fields record local softening and failure that could be caused by warm, briny zones. Each of these features is a possible point of contact between the surface and the internal water system. They are not open vents in most cases. They are structures that can allow material to move when the stress and temperature conditions align. If plumes of water vapor sometimes erupt above Europa, as some observations suggest, they would connect the ocean or near-surface reservoirs to space. A plume would carry water molecules, salts, and organic compounds upward. Instruments that pass through such a plume can measure composition directly. They can look for dissolved substances and for ratios of isotopes that reveal the history of the water. Isotopes are atoms of the same element with different masses. The ratio of deuterium to hydrogen in water, for example, can hint at sources and processes. The presence or absence of specific salts can hint at the kind of rock-water reactions happening below. The question of habitability depends on the steady availability of liquid water, sources of energy, and essential elements such as carbon, nitrogen, sulfur, and phosphorus. The magnetic and structural evidence points to long-lived liquid water. Tidal heating provides energy within the ice and the rock. Reactions at the seafloor can add more energy and feed dissolved molecules into the ocean. The surface, under radiation, produces oxidants and shows signs of salts and carbon-bearing compounds. The missing piece is the rate and the routes of exchange between the surface, the shell, and the ocean. That exchange is not an afterthought. It is a central part of Europa's system. If oxidants made in the top millimeters reach the ocean, they can drive redox chemistry for very long times. If salts from the ocean reach the surface, they can tell us about the interior without drilling deep. If shallow brines move within the shell, they can build the ridges and pits that we step around and study. The ocean, the ice, and the surface are linked by cracks, bands, and slow overturn. The evidence for a hidden ocean and for internal energy sets the stage for tracing those links with care. How does material move between Europa's surface and the hidden water below? Radiation at the surface starts the story. Fast particles from Jupiter and sunlight with enough energy strike Europa's bright ice and split water molecules. From this breaking, reactive products form. Two important products are oxygen and hydrogen peroxide. These products are called oxidants because they tend to take electrons from other substances during reactions. In simple terms, they are chemical packets of stored energy. They build up in the topmost layer of ice, mainly within the upper millimeters and centimeters, where radiation is strongest. The making of these oxidants never stops while radiation continues to arrive. The rate changes from place to place. The trailing side, which faces backward along Europa's orbit, receives more particle hits and likely makes more oxidants. The leading side likely makes fewer. This uneven production lays down a patchwork of chemical potential right on the skin of Europa. Evidence for other chemicals at the surface comes from how the ice reflects light at different colors. Instruments can read these color patterns and match them to known substances. Signals across wide regions point to salts. Two common candidates are sodium chloride and magnesium sulfate. The first is the compound many people know from common salt. The second is a salt that forms when magnesium and sulfate come together. The precise amounts are not settled, but the presence of salt is supported by many measurements. These salts could be leftovers from older events that brought material upward. They could also be products formed in the ice itself after radiation and mixing. In 2023, a study mapped carbon dioxide in a region named Terra Regio. The pattern of that carbon signal followed the outline of a geologic unit rather than a random smear. That kind of match suggests a source from within the shell rather than only arrival from space. Carbon compounds at the surface matter because carbon is part of many important molecules, including those that can serve as food for chemistry that uses the oxidants. The surface is not a sealed lid. Cracks and bands break it. Earlier, we traced how stress from Jupiter's pull can open and close fractures on a slow clock, and how salts can keep small pockets of liquid stable at shallow depths. These features are more than shapes. They are conduits that can connect the surface to the ice below. When tension opens a crack, frost can fall inward. Oxidants can follow the crack walls. When compression closes the crack, the walls can crush down and trap thin films of new material. Repeating this many times can drive surface products downward step by step. Double ridges add a clear piece to this picture. Many stand as two long, narrow hills with a central trough. A strong idea for how they form is that a pocket of briny water sits only a few hundreds of meters below the surface. Stress opens a path. Liquid moves toward the path. The pocket refreezes. When salty water freezes, it releases heat and expands a little. The expansion pushes outward and upward, lifting the sides into paired ridges and leaving a lower channel between them. The details can vary, but the core elements tie mechanics to chemistry. A salty pocket remains liquid because salt lowers the freezing point. Freezing then moves ice and records the event in the ground. The depth of a few hundreds of meters matters. It is shallow enough that tides can open and close fractures above it. It is deep enough that the pocket can persist without boiling away into the vacuum. Wide bands record a slower form of exchange. When the shell extends, a gap can open. Soft, warm ice or slush from below can rise into this gap and solidify. The interior of such a band often looks darker and rougher than the country around it. If the material carries salts or other dissolved compounds from deeper layers, the band can become a repository of chemical samples from within the shell. Some bands display subtle ridges and textures inside that align with the edges, pointing to stepwise growth. The dark tone is not proof by itself of origin, but color and spectral signals that match salts and carbon compounds make the case stronger. Chaos terrains tell of events that can mobilize ice and brine together. In these regions, blocks several kilometers across have rotated and settled into a matrix that later refroze. That matrix could have been thick slush. Slush can carry dissolved substances. If the disruption reached down into a zone rich in brines, it could have lifted that material upward, closer to the surface. After refreezing, the chemistry can remain in place for long times because there is no weather to wash it away. Radiation will alter the very top, but if fresh blocks or band interiors are young relative to surrounding ground, they can preserve sharper chemical signals. The direction of movement is not only upward, the surface also sends products downward. This is important because oxidants at the top hold energy that chemical systems can use. For that energy to reach the ocean, a delivery path must exist. One path is through cracks and veins that carry brines deeper as they freeze and melt on cycles. Another path is through slow overturn of the ice shell. Overturn means that older ice can sink while younger ice forms above and spreads. A more specific version is subduction. Subduction means a slab of surface ice moves downward into the shell under another slab. The process would be slow on Europa, but even slow rates matter over long times. If slabs carry oxidants, they can deliver those chemicals to layers where brines gather, and from there to the ocean. Rates and amounts are the biggest unknowns. How much oxygen and hydrogen peroxide form per square meter each day depends on radiation dose and ice properties. How much of that remains stable and how much is destroyed or reworked by further radiation depends on time and temperature. How much then travels downward in cracks depends on how wide and how frequent openings occur at a given place. How many slabs subduct over 1,000,000 years depends on how often stress focuses at plate boundaries in the shell. These questions do not yield quick answers, but they can be addressed with steady observation and careful models. There are tests we can run from a distance. Maps of hydrogen peroxide and oxygen at the surface can show where production and retention are strongest. If these maps correlate with fracture networks, it suggests frequent exchange. If they correlate with band interiors, it suggests older deliveries that are now frozen in place. Spectral maps of salts can show where sodium chloride and magnesium sulfate concentrate. If salt patterns align with chaos regions and bands rather than uniform planes, it supports upward transport during events. The carbon dioxide map at Terra Regio already fits that kind of pattern. Adding new regions to that kind of survey extends the test. Thermal data help too. If near-surface pockets of liquid exist, even briefly, they change how the surface warms and cools during the long day. A ridge fed by shallow brine can show subtle differences in temperature at local noon and after sunset compared to ridges without such feeding. If a band retains higher porosity or different grain size because of how it formed, its thermal inertia will differ. Thermal inertia describes how slowly a material's temperature changes. Watching the pace of heating and cooling over many hours gives clues about structure and about recent activity. Another test looks upward rather than downward. In a place with almost no air, any gas released from the surface will spread freely and thin quickly. Even so, a sensitive instrument above the surface can measure faint gases. Oxygen from radiation is present near the ground. If a crack opens, tiny extra amounts can escape. Hydrogen peroxide and other short-lived products can break down and feed oxygen. If briny liquid refreezes near the top of a ridge, it can release dissolved gases. Detecting such bursts is difficult because they are small and short. But if timed with the stress cycle that opens and closes cracks, the odds improve. Watching candidate features during times of predicted tension can catch these events. Isotopes add another layer of insight. Isotopes are versions of the same element that have different mass. Hydrogen has a heavy version called deuterium. The ratio of deuterium to hydrogen in water carries information about sources and processing. If water from a plume carries a ratio that matches what we expect from the ocean, it strengthens the link to the interior. If it differs and matches what we expect from near-surface processes, it points to shallow sources. Similar checks can be applied to carbon in carbon dioxide. Ratios of carbon isotopes can distinguish between products from space dust, from internal processes, or from surface chemistry. These measurements require careful instruments and careful correction for background signals in Jupiter's space environment. The balance between oxidants from above and reduced compounds from below is central. Reduced compounds are substances that tend to give up electrons during reactions. Water reacting with rocks at the seafloor can produce hydrogen and other reduced molecules. When these meet oxidants from the surface, reactions can release energy. These are known in simple terms as redox reactions. If exchange is steady, such reactions can continue for very long periods and can maintain chemical gradients throughout parts of the ocean. If exchange is weak, the gradients will be smaller and limited to areas near vents on the seafloor. Reading the landscape of Europa's ice tells us where exchange might be stronger, because it tells us where paths exist. The chemical story connects to mechanics in practical ways. Consider a double ridge that shows fresh frost and dark streaks along its trough. Fresh frost hints at recent opening and refreezing. Dark streaks hint at concentrated impurities. A plan to study exchange at this ridge would align observations with predicted stress peaks. It would pair imaging to track changes in brightness with spectrometers to watch for oxygen and hydrogen peroxide signals. It would include a pass from an instrument that can sample gases above the surface. It would schedule thermal scans through the long day to see if parts of the ridge hold heat differently. The same plan applied to a chaos edge would look for similar signs but would adjust for rougher ground and for a more complex mix of surfaces. Deep exchange can move in the other direction as well. If the ocean feeds brines upward into the shell, the ice above will reflect that in composition. Salts do not all move the same way. Some stay dissolved more easily, some crystallize and stay behind during freezing. If a shallow lens of brine formed by partial freezing of ocean water feeds a ridge, the salts in that lens will reflect that specific history. By comparing salt types across many features, we can infer patterns of freezing and melting under the shell. This is a slow form of reading, but it is grounded in measurable properties. An important caution is that space weathering can change surface chemistry without any exchange with the ocean. Radiation can break and remake molecules. Micrometeorites can deliver exotic compounds in tiny amounts. Without careful checks, we might mistake a changed surface for a delivered sample from below. That is why patterns that match geologic units, like the carbon dioxide in Terra Regio, are valuable. They argue against uniform coating from outside and toward internal links. Still, skepticism remains healthy. Independent lines of evidence should agree before strong claims are made. The thin oxygen layer near the surface reacts to this cycling. Oxygen is both a product at the top and a participant in reactions within the shell. If oxidants travel downward, the oxygen density near the surface could fall slightly at times and places where delivery is active. If refreezing vents bring up gas from shallow brines, local oxygen density could rise briefly. These are subtle signals against a dynamic background, but they are part of the picture. Instruments that can map oxygen over regions and days can search for small, repeatable changes tied to known features. Exchange through slow overturn may be the largest long-term contributor. If parts of the shell dive and new ice forms elsewhere, then the surface becomes a conveyor over geologic time. Oxidants embedded in the top centimeters can be carried down by meters every long cycle if the process is active. This is not fast on a human clock, it is steady on the clock of a moon. Evidence for such sinking would include bands and margins where one plate appears to pass under another, faint scrapes that align with movement, and mismatched heights that persist along contacts. Some of these signatures have been reported in various regions. Their presence keeps the idea of subduction on the table while details of rate and extent remain under study. All these processes together build a network of paths. Some are short and shallow and work in step with the daily and orbital tide. Some are long and deep and work over ages. Through these paths, oxidants formed at the very top can reach pockets of brine in the shell and possibly the ocean. Through these paths, salts and carbon compounds from the ocean can reach the surface. The presence of salts and carbon dioxide in specific terrains supports upward movement. The presence of ridges and fractures that open and close supports downward movement. The challenge is to measure the flow rather than only the pathways. A way to catch the flow directly is to study any material that leaves the surface into space. Gas that escapes from an opening, even for a short time, carries a sample of the chemistry inside. Tiny grains of ice lofted with the gas carry trapped salts and organics. If sensors can cross those paths and count molecules and grains, they can read composition with little ambiguity. The timing of such crossings would follow the stress clock and target features already mapped as active. When internal water reaches the space above the ice in this way, the exchange becomes visible as a set of signals that instruments can chase across the sky and tie back to the ground below. How do you catch water and salt in space without landing? If material sometimes escapes from Europa, it becomes a direct sample of the inside. Gas and tiny ice grains leave the surface and rise for hundreds of kilometers when a plume is active. In the near vacuum around Europa, this material expands freely and thins quickly. It may last for only minutes to hours and then it is gone. To learn from such brief events, a spacecraft must be in the right place at the right time and must carry the right tools. This is a demanding task, but it builds on what we already know about stress in the ice, shallow pockets of brine, and cracks that open and close on a slow clock. Reports of plumes come from two kinds of observations. One kind is remote. A telescope in space has seen faint features in ultraviolet light above Europa on a few occasions. Ultraviolet is light with shorter wavelengths than blue light, invisible to the human eye. Those features have the shape and position expected if water vapor rose high above the surface and was split by sunlight into hydrogen and oxygen. The other kind of hint is local. During one close pass years ago, a spacecraft measured changes in the plasma around Europa that fit the idea that it moved through a patch of extra gas and dust. Plasma is a gas of charged particles, such as electrons and ions. None of these signs were long and steady. They were short and rare. That is not a problem. It simply tells us that any plan to sample plumes must accept that activity may be intermittent and must be ready to take advantage of brief chances. The surface story points to where and when plumes are most likely. Cracks widen when Europa is under tension from Jupiter's pull and narrow when compression comes. Double ridges with central troughs and chaos margins are tied to shallow brine pockets that can refreeze and push ice upward. These are natural places to watch. Stress predictions give times in the long day when cracks are more likely to be open. A plan that lines up a low pass over a target ridge during a predicted tension phase has a better chance to see gas rising or to cross a thin plume. Spacecraft that study Europa now aim to make many close passes rather than to stay in orbit around the Moon. The reason is simple. Radiation near Europa is strong. A spacecraft that orbits Jupiter and dives down to skim Europa keeps its total dose lower while still gathering detailed data each time it passes. Over many passes, a global picture forms. Each pass can be tuned to a different goal. One may focus on a likely plume source in daylight. Another may pass over the same area at night to look for thermal signs. Another may fly over a different region to build the map of ice layers. This rhythm builds knowledge without staying in the harshest zones for long. Plume sampling needs specific instruments. A mass spectrometer can count and identify molecules in the gas. It works by taking in a sample and weighing the molecules by how they move in electric and magnetic fields. With a well-designed inlet, it can tell water apart from oxygen, hydrogen, carbon dioxide, and other gases. It can also read the ratio of deuterium to hydrogen in water. Deuterium is a heavy form of hydrogen. The ratio of deuterium to hydrogen helps trace the history of the water because different sources and processes leave different ratios. Another useful tool is a dust or particle analyzer that can catch tiny grains of ice and read their composition as they vaporize and are weighed. Grains carry salts and organic molecules trapped inside. Measuring them tells us what dissolved materials are present in the source liquid. Other sensors add context. A magnetometer measures the magnetic field. It can see changes caused by currents in the plasma near Europa and can improve models of the hidden ocean. A plasma instrument counts electrons and ions and measures their energies and directions. When a spacecraft passes through a plume, the plasma environment changes in a specific way. Water molecules and their fragments can pick up charges and change the counts. A camera with high sensitivity can try to image a plume against space when the spacecraft passes near the limb, which is the edge of the disk. A spectrograph that reads light by color can look for the fingerprints of hydrogen, oxygen, and water products in ultraviolet or infrared light. Ice-penetrating radar maps the structure beneath the surface and can point to shallow pockets aligned with surface features that may feed plumes. Timing affects all of these tools. A low pass moves quickly. A spacecraft can be over a target region for only a few minutes. Exposure times must be short. Sample inlets must be oriented into the direction of flight to collect enough material. Commands should be simple and mostly automated because light takes a long time to travel between Earth and Jupiter. The two-way delay can exceed half an hour. This means the spacecraft must make decisions on its own based on pre-planned rules. If a detector sees a sudden rise in water counts, it can switch to a high-rate sampling mode. If it does not, it can continue with the planned survey. False signals are a real concern. A spacecraft is not a clean rock. It breathes out small amounts of gas from its own materials, a process called outgassing. Thrusters fire and throw out exhaust that contains water and other molecules. Radiation can also make detectors glitch. To keep trust in the data, teams plan careful checks. Instruments run background scans far from Europa to measure the spacecraft's own signature. They take blanks during the pass and after it. They compare directions. Plume material should arrive from a fixed direction tied to the flight path and location. Spacecraft gases tend to follow different patterns. Instruments may warm and then cool their inlets in a controlled way and watch how counts change. Real environmental signals should not depend on such heater cycles. These simple tests help separate environment from self. Flyby geometry can help with contamination control. If the spacecraft approaches with a clean side forward and keeps thrusters idle during the key minutes, the chance of sampling its own exhaust is reduced. After the pass, a turnaround and a short burn can put it on a safe path away from Europa. Careful pointing keeps sensitive detectors out of the direct radiation from Jupiter when not in use. Shields and placement of components inside the body of the spacecraft reduce damage from energetic particles. These practical choices extend the life of instruments and keep their readings stable. Even when a plume is not seen, the flyby adds value. Instruments can measure upper limits on gas near the surface. An upper limit means the highest amount that could be present without being detected. This constrains how often and how strong any plumes can be. Cameras can watch for new frost or dark spots laid down since the last pass. Thermal cameras can look for warm patches that would hint at near-surface liquid. Radar can map layers and look for lenses that might feed ridges. Magnetometers can refine models of the ocean and the ice shell. Little by little, uncertainty shrinks and predictions become sharper. When a plume is seen, the data become a chain from inside to outside. Gas composition tells us what dissolved molecules were present in the source. Grain composition tells us what salts are in the brine. The ratio of deuterium to hydrogen in water tells us about the history of the source liquid. Ratios of oxygen isotopes and carbon isotopes can, in principle, distinguish between external delivery and internal origin. If carbon dioxide is present in the plume and the surface below already shows a carbon dioxide signal, the link strengthens. If a plume is sampled over a ridge or a chaos margin with known salt signatures, we can tie the sample to the geology with confidence. The distribution of plume material also leaves marks on the ground. When gas and grains fall back, they can frost a patch. That patch should be downwind only if significant winds existed, but there is almost no air, so the pattern is controlled by the direction of ejection and by gravity. Ballistic paths are simple arcs. Mapping fresh frost around a suspected source can therefore reveal the direction and strength of the event. If this pattern changes with the stress cycle, it becomes an extra clue. A ridge that frosts its sides after a predicted tension phase could be venting when it opens. Repeated observations can test this with clear before and after images. The choice to favor repeated flybys also shapes the design of the mission path. The spacecraft must loop around Jupiter in a way that brings it past Europa many times at various longitudes and latitudes and at different times in Europa's long day. Some passes should be low, at tens of kilometers to a few hundred kilometers altitude, to sample gases and grains. Others can be higher to give time for broad imaging and to reduce risk from particle impacts. The sequence should cover the leading side, the trailing side, the inward face, and the outward face. This coverage will map how radiation, stress, and composition vary across the globe. Communication and data handling need care. Sampling at high speed can produce bursts of data that exceed the link capacity if not managed. Onboard storage must hold the data until it can be sent during later, calmer times when the spacecraft is far from Europa. Error checking protects data against bit flips caused by radiation. Redundant storage and cross-checks catch and repair errors. These may sound like technical details, but they are the difference between a hinted feature and a solid measurement. Coordinated observations improve confidence. A ground or space telescope can watch Europa in ultraviolet before, during, and after a planned pass. If it sees a faint ultraviolet glow above a target region, the spacecraft can tilt its instruments to sample that region. Even if the glow is not seen, the pass can still go forward. The telescope data then becomes a clean non-detection that tightens limits. On the spacecraft, instruments can coordinate too. A rise in water counts can trigger a camera to take a quick set of images of the limb. A change in plasma density can trigger a magnetometer to increase its sampling rate. These crosslinks make the most of short windows. The path from a plume to a wider understanding runs through composition. Salts like sodium chloride and magnesium sulfate carry stories about water-rock reactions at the seafloor and about freezing and melting in the shell. Organic molecules, if present, have patterns that can reveal whether they formed in simple water-rock chemistry or were altered by radiation near the surface. The presence of ammonia would lower the freezing point and hint at different chemistry. The absence of certain species is also important. If no organics are found, despite careful searches and strong sampling, that tells us about the ocean's history and about the efficiency of radiation in destroying molecules at the surface and near the top of the shell. Plume studies also measure processes in space near Europa. The thin oxygen layer above the surface interacts with the plasma trapped by Jupiter's magnetic field. A plume adds neutral gas to this space, which then gets ionized and joins the plasma. This changes how particles move and how fields behave. By measuring these changes, we learn how Europa's space environment works. This helps us correct for background effects when we interpret surface signals and ocean signals. It also informs designs for future missions that must operate safely in this environment. The knowledge gained from flybys guides choices on the ground. A map of active and quiet ridges tells us where to aim for fresh material and where to avoid fragile zones. A catalogue of dose measurements tells us where radiation is most intense and where it is less intense. A record of frost fallbacks after plumes suggests where the surface may be softer or more porous due to repeated deposits. Radar maps of shallow lenses under likely source features tell us which sites may have near-surface liquid. All of this informs site selection, approach paths, and timelines for any attempt to touch the ice. There is value in restraint. A flyby program can test claims of activity carefully, log null results honestly, and keep clear standards for detection. This attitude protects against errors and builds a reliable base for later steps. It is also consistent with the rules that govern clean exploration. If a plume can be sampled from space, it reduces the pressure to drill or melt until designs are ready and cleanliness is proven. It gives science data while avoiding contact with the ice. When the time comes to land, the mission can carry a more accurate picture of hazards and a cleaner plan for how to work. Plumes are not the only target during flybys, but they are a strong link between surface geology and interior chemistry. Each pass that crosses a plume converts invisible exchange into measurable numbers. Each pass that does not cross one narrows the range of how often and how much Europa vents. With many passes, patterns emerge. Are plumes tied to certain longitudes or latitudes? Do they favor the trailing side or the leading side? Do they cluster near bands or chaos regions with known salt signatures? Do they switch on at predictable times in the tidal cycle? Answers to these questions connect the map of stress and ice behavior to the map of chemistry and to the properties of the ocean. As this picture sharpens, attention turns naturally to the surface itself. The ground is rough, cold, and bright. Radiation limits time. Traction is poor. Yet the same features that complicate movement also mark places where the ice is most informative. The choice to send a craft down to the ice brings a new set of needs. The craft must grip hard ice, keep warm without melting its footing, and work quickly under a tight radiation budget. It must also be clean and designed to leave the site safe. The knowledge from flybys makes these tasks more realistic by pointing to safer places, better times, and richer targets. What would it take to touch Europa's ice without harming it? A lander on Europa must accept the place as it is. The ground is hard ice. The air above it is almost nothing. Light is weak. Radiation is intense. Time on the surface is limited. Yet the same ground holds fresh records of recent activity, and it may hold chemistry that speaks about the ocean below. The path forward is to design a craft that can grip, endure, measure, and leave the site clean. Descent is the first challenge. Thrusters provide control, but hot exhaust can heat and pit the ice. That would alter the very surface we want to study. A careful profile keeps thrust low near the ground. Short pulses or cold gas jets can finish the descent. Legs must spread weight and absorb the small impact that remains. The craft must sense tilt and touch at each foot. If a foot lands on a small block or on the edge of a trough, the system must adjust and settle without sliding. Cameras and laser rangefinders watch for ridges, pits, and cracks during the final seconds, but decisions at this stage must be fast and simple. Autonomy takes over because radio commands from Earth would arrive too late. Once down, the lander must hold itself in place. On hard ice, friction alone is not enough. Anchors are needed. Ice screws can bite into solid ice. Harpoons can set quickly into near-surface layers. Small spikes on each foot help prevent sideways drift. The sequence matters. First, the feet settle. Then, light anchors go in to test the ground. If the ice holds, deeper screws can engage. Each anchor should measure the force it carries. That way, the craft knows how much grip it has and whether it needs to adjust. The top skin of Europa's ice is brittle. A single strong push can crack it. Anchors that spread load are safer than anchors that focus stress. Spacing anchors apart and tightening them in steps reduces the chance of starting a new fracture. Thermal control runs through every task. Sunlight gives little warmth and radiation takes it away into space. Power will come from nuclear heat sources because days are long and sunlight is weak. These sources produce steady heat whether instruments are on or off. That heat must keep the core of the lander warm, but must not melt the ice under the feet. Melt under a foot can refreeze unevenly and cause tilt, or it can create a thin layer that reduces grip. Designers can route heat into radiators that face the sky and away from the ground. They can insulate the legs and add standoffs that reduce direct heat flow into the ice. They can schedule power-hungry tasks during times when radiators are most effective, such as when the sky above is clear and cold, and the sun's angle allows efficient heat rejection. Power systems must be simple and steady. Nuclear heat sources such as radioisotope units give continuous output. Batteries store energy for short bursts. The system must balance science activity against thermal limits and communication windows. When instruments that need heat, such as ovens in a mass spectrometer, are active, the rest of the craft can shift to low power to keep the overall thermal load within safe bounds. When the long night begins, heaters hold the temperature of sensitive parts. All of this is planned in advance with margins for the unknown. Communication is its own discipline at this distance. The time for a radio signal to go to Europa and back can be more than half an hour. Data rates are low so far from the sun. The lander cannot wait for instructions in the middle of delicate moves. It must be able to anchor, sample, and recover from small slips on its own. It must store data securely until a relay craft or Earth is in view. It must decide which data to send first if radio time is short. A simple rule works well here. Send a short summary that shows time, place, and status. Follow with the most valuable science data. Keep a copy of everything until an explicit confirm arrives. Use error checking on every packet. Test for bit flips and correct them. Repeat sends if a check fails. Radiation is a steady presence. It can harm electronics slowly through total dose and suddenly through single strikes. The lander carries shielding around key parts. It uses parts that are tolerant to dose. It spreads critical functions across separate units. If one fails, another can continue. Memory uses error-correcting codes that can detect and fix a bit flip. Processors use watchdog timers that force a clean restart if the system becomes confused. Sensors can show false spikes when a particle hits. The software knows how to ignore a single bad point and to trust only patterns that persist. Shielding mass is precious. Designers put it where it matters most and accept higher risk for parts that are easy to replace in software, such as non-critical sensors. Operations on the surface follow a simple rhythm: anchor, survey, sample, analyze, transmit. Each step includes checks for traction, heat, and dose. Anchor loads are watched, foot temperatures are watched, radiation counters are watched. If a limit nears, the lander stops and goes to a safe state. A safe state keeps the craft warm and upright and waits for a new plan. Few moves are better than many. Short distances are better than long. The craft does not roam the terrain. It reaches, leans, and returns to center. Sampling needs tools that can work in hard ice without throwing debris or heating the ground too much. A short corer can bite into ice and bring up a plug. A micro drill can shave a small cavity and collect cuttings. A scoop can gather loose frost and grains if present. Every tool that touches ice must be clean before it ever sees Europa. Clean here means sterilized to a strict level. The parts are assembled in controlled rooms. They are heated, exposed to sterilant gas, or bathed in radiation under set procedures that kill resistant spores. They are sealed until use. Seals break only once. Witness plates are carried. These are surfaces inside seals that are opened at the same time as the sample path. They record any contamination from the craft. During analysis, instruments test these witness plates as blanks. If they show a signal, it shows the system itself is dirty, and the data must be interpreted with that in mind. Life detection needs more than a single signal. It needs independent lines of evidence that agree. One line is structure. A microscope can look for cell-like shapes or for repeating microstructures inside the ice that are not explained by simple freezing. Another line is chemistry. A mass spectrometer can look for complex organic molecules with patterns that are not produced by non-living chemistry under known conditions. It can look for sets of molecules that appear in specific ratios. A third line is gas balance. An instrument can heat a sample slightly and watch what gases are released and in what amounts. A mixture very far from simple chemical balance can be a clue, though not proof. A fourth line is isotopes. Ratios of isotopes, such as carbon-13 to carbon-12 or deuterium to hydrogen, can point to specific processes. If several lines point in the same direction and if blanks and standards are clean, confidence grows. Standards are reference samples carried on board. They are sealed and clean. Instruments test them to confirm that the instruments read expected values. Blanks are empty runs that test the system for background. These checks prevent false positives. They also reveal drifts in sensors. If a standard reads off-target, the instrument can be recalibrated, or the error can be recorded and corrected in the analysis. This discipline is essential in a place where every sample is precious and cannot be repeated easily. Going deeper than a short core is a different class of effort. Melting a path through ice over many kilometers takes great energy. To melt down 20 kilometers would need on the order of 100 trillion joules, not counting losses. Losses in a real system would be large. A melt probe, sometimes called a cryobot, uses heat at its nose to melt ice and sinks under its own weight. A tether pays out from the lander, carrying power and a fiber for data. The meltwater refreezes behind the probe, closing the path. This seals the tether into the ice and protects it from the open environment. The probe must keep the tether from freezing to the walls and must avoid refreezing its own nose if it slows. At salt layers, the freezing point changes. At places with debris, the nose can clog. A melt probe must carry sensors to measure chemistry and conditions as it descends, because radio waves do not travel through thick ice. If it reaches a brine lens or the ocean, it must be clean enough not to harm it, and it must be able to turn and explore a little, then send data back through the fiber. Building such a system is a long effort that requires years of testing under ice on Earth to learn how to handle refreezing, tether drag, and contamination. A mechanical drill is another concept. A drill uses cutting heads to grind ice and can deliver sterile fluid to carry cuttings away and to prevent refreezing at the bit. The fluid must be sterile, must not react with the environment, and must remain contained. The drill string, which is the chain of parts that carries power and torque down the hole, must be sealed and clean. Valves must prevent backflow. Sensors must watch for leaks. At chosen depths, valves can open briefly to take a sample into a sealed chamber. Once full, the chamber closes and travels back up the bore with the cuttings flow. The entire column must be handled without exposing the inside to the surface. This is complex. It can be done, but it demands strict cleanliness and simple, robust parts. Cleanliness is not only a technical choice, it is required by law and by shared agreements. The Outer Space Treaty asks all states to avoid harmful contamination of other worlds and to avoid adverse changes to Earth if material returns. Rules for icy worlds are strict because the chance of liquid water and useful chemistry is high. Land emissions to Europa fall into a high protection category. That means careful accounting of the total number of microbes on the craft before launch, validated sterilization steps, sealed paths for anything that contacts ice, and a plan for what happens at the end of the mission. The plan should prevent the craft from drifting or being blown by a later eruptive event into a region where it could cause contamination. For orbiters and flyby craft, the plan often calls for a controlled plunge into Jupiter at the end of life, where heat destroys the craft completely. For landers, end-of-mission steps can include heating and sealing sampling paths, opening valves that vent internal gas and collapse lines, and disabling any pressure sources. The goal is to leave nothing that can later leak into the environment. Operations far from Earth must be resilient. Autonomy handles many tasks. The lander detects a slip and increases anchor tension. It senses that an anchor is cutting through and relaxes for a moment, then tries a new depth. It notices a rise in radiation and pauses an instrument with non-essential exposure. It checks that a sample cup is sealed before heating. It avoids heating that would melt its feet. It detects that a drill motor draws too much current and backs off to clear chips. These are small, local decisions that protect the mission and the site. Data handling has its own safeguards. Critical data are stored in two places. A summary is sent first. Longer files are compressed and queued. If a file fails to deliver completely, it is sent again during the next window. Logs include time marks tied to Europa's long day so that patterns can be tied to stress cycles and temperature cycles. Radiation counters log dose with location so that every reading can be weighted by the environment at the time. Even with careful design, some plans will not work perfectly on the first try. That is why tests with blanks, standards, and witness plates are so important. They provide truth checks when the environment is noisy and the stakes are high. It is also why designs include simple tools alongside complex ones. A camera can see frost and color. A thermometer can read heating and cooling. These support the interpretation of advanced mass measurements and microscopic images. When results from different instruments agree, confidence grows. A lander does not need to work for months to add value. The environment is harsh, and radiation sets a tight upper bound on safe time. A few days of smart, disciplined work can answer focused questions. Is there fresh chemistry in this ridge trough? Does this chaos margin hold salts that match those seen from orbit? Do gases rise during predicted tension at this fracture? Are complex organics present near a band interior, and do they show patterns that are not matched by blanks? Each answer narrows the range of what is possible inside Europa and informs the choice of future steps. Subsurface access at scale will demand new power systems, new materials, and even stricter cleanliness. The energy needed to reach deep water is large. The engineering to operate over many kilometers in ice is demanding. Clean assembly and sealed handling from start to finish are essential. These needs are clear and concrete. They can be met with sustained work and with steady testing in places on Earth that mimic some parts of the problem. Along the way, safer electronics that correct their own errors, power systems that stay stable for years, anchors that place and retract without cracking hard ice, and manufacturing lines that deliver sterile gear will all improve. With these pieces in place, deeper access can be attempted with care that matches the stakes. When a lander stands on Europa, even for a short time, it turns maps and spectra into touch and sample. It tests stress forecasts with anchors and readings. It tests chemical maps with real ice. It tests protection rules with practice and with proof. From that ground truth, future plans can be built on firmer soil, even if that soil is frozen water. How do you explore a place like Europa step by step, without rushing and without causing harm? A lander that touches the ice for a short time is only one part of a larger plan. The wider plan links many kinds of missions and many kinds of tests into one steady path. It uses what we have learned about the orbit, the slow day and night, the deep cold, the radiation, the surface patterns, the way ice behaves, the hidden ocean, and the chemical exchange through cracks and ridges. It then turns this knowledge into schedules, tools, rules, and checkpoints. The goal is simple: learn honestly, work safely, keep the environment clean, build confidence before moving deeper. The first layer is a long series of close flybys. Each pass adds a piece. Together, they make a coherent picture. Instruments look down and look around. Ice-penetrating radar maps layers in the shell and finds buried structures that line up with ridges, bands, and chaos fields. A magnetometer reads the time-varying magnetic field and refines estimates of the ocean's depth and salt content. A mass spectrometer and a dust analyzer sample gases and tiny grains when a pass crosses a suspected plume. Cameras and spectrographs build maps of brightness, color, and composition under many sun angles and many longitudes. A plasma instrument counts charged particles and tells how Europa's thin oxygen layer and any plume change the space around the moon. Each pass repeats some views and adds new ones. Together, they shrink uncertainty about where liquid is shallow, where stress is high, and where chemistry at the surface looks fresh. Timing is as important as the tools. Cracks and troughs respond to a slow tidal clock. They open a bit during one phase and close a bit during another phase. By planning passes at different hours of Europa's long day and at different positions in the orbit, teams can watch the same features under different stress. When maps from these times are compared, differences that match the predicted stress cycle carry special weight. A rise in gas above a ridge when tension is expected, a subtle thermal change near a band during the same phase, and a clean absence of changes during compression are the small linked signs that support a living picture of exchange in the shell. This flyby stage defines decision points. If repeated passes see water vapor with salts and organic molecules over a specific region, and the timing matches tidal stress, the case to return to that region in more detail becomes strong. If radar shows shallow lenses that align with double ridges, and surface spectra show salts and carbon dioxide in those lanes, the case to study these corridors intensively becomes strong. If none of these signs appear after many passes, the plan shifts. It turns to broader mapping to constrain how deep the ocean lies and how thick the brittle lid is, and to a wider search for any signs of activity in new places. A null result is not a failure. It removes options that are not supported by data and saves effort for paths that remain plausible. While the flybys build knowledge, key technologies mature on the ground. Electronics must work under high radiation. Engineers build and test circuits that keep working after absorbing large doses, and that can detect and correct single-bit errors caused by particle strikes. This is often called radiation hardening. In simple words, it means parts that keep their function in a harsh field and that can fix small mistakes as they happen. Power systems must be stable and compact. Small heat sources that run for years and careful power management keep instruments warm without melting the ground under a lander. Anchoring systems place and retract without cracking brittle ice. Feet that spread load and screws that grip with modest pressure replace tools that would gouge and split the crust. Clean assembly becomes a program in itself. Parts that will touch ice or liquid are built in controlled rooms. They are sterilized by heat, by gas, or by radiation using methods that are validated with test organisms. They are sealed until use. Interfaces are designed so that seals are intact until the exact moment of sampling. Tracing of microbial counts is done part by part and documented. This is not a last-minute add-on. It is a line of work that starts years before launch because cleanliness must be proven and repeatable. The same care applies to ground labs that may someday handle returned material. The rooms, tools, filters, and training for such work can be prepared long before any sample exists. This preparation reduces risk and builds shared trust. As instruments and practices mature, the program adds low-altitude sampling passes that aim for short windows over likely active regions. These flights are brief, direct, and focused. They approach with clean inlets open and thrusters idle. They cross the target, gather gas and grains, and climb away. The mass spectrometer reads water, oxygen, carbon dioxide, and many other species. It also reads ratios of isotopes such as deuterium to hydrogen in water and carbon-13 to carbon-12 in carbon dioxide. The dust analyzer reads salts in grains and scans for organics. The plasma and magnetic sensors record changes that confirm the crossing of a gas cloud rather than a false signal from the spacecraft itself. The camera takes limb images to catch a faint plume if present. These passes either confirm activity or set strict upper limits on how often and how strong any plumes are. Both outcomes guide the next steps. With these data in hand, a short-lived lander can be sent to a site that meets several conditions. The site is geologically meaningful, for example, a double ridge that shows fresh frost and salt signatures, or the edge of a chaos field with signs of refrozen slush. The site is also within safer ranges for radiation compared to the harshest zones. The light and terrain allow a clean descent and stable footing. The lander carries tested anchors, clean sampling tools, and simple, robust instruments. It anchors, surveys, samples, analyzes, and transmits, all within a tight time and dose budget. The analysis uses blanks and standards on board to check for false signals. Any hint of organics is checked against witness plates and against the lander's own signatures. Any gas release during the predicted tension phase is logged with timestamps tied to the tidal clock. This is not a marathon. It is a short, careful visit that grounds the maps with direct measurements. Deeper access can follow only when power systems, thermal systems, and cleanliness reach proven levels. Reaching shallow brine pockets a few hundreds of meters below the surface requires far less energy than melting through tens of kilometers, but it still demands steady heat and safe control. A melt probe that aims for a shallow target must keep its nose just warm enough to move, keep its tether free, and keep its path sealed. A drill that aims for a shallow target must keep its fluid sterile and contained. Sensors on the probe or drill must read chemistry along the way, because return to the same path will be hard. These efforts must begin on Earth in thick ice, under vacuum and cold, so that problems with refreezing, clogging, and seals are found and fixed before flight. All along this path, policy keeps pace with engineering. The Outer Space Treaty sets the shared duty to avoid harmful contamination. The specific guidance for Europa sets strict requirements that affect design from the first sketches. They also affect end-of-mission plans. An orbiter that finishes its work should be sent to burn in Jupiter so that it cannot hit Europa later. A lander that finishes should seal its lines, vent its pressure sources, and enter a quiet state that does not leak. If a sample ever comes back to Earth, it must enter a high-level lab designed to protect both the sample and the outside world. Chain of custody methods must be clear. Chain of custody means a complete, documented record of where the sample was, who handled it, and how it was kept clean and intact. This level of rigor sustains public trust and scientific value. Science planning benefits from coordination and openness. When radar, magnetometer, imaging, and in situ sampling are aimed at the same region within a narrow span of time, the results cross-check each other. When observations are scheduled near expected stress peaks, small signals are easier to interpret. When data, methods, and calibration files are shared quickly and in standard formats, teams in many places can test ideas and find errors faster. Open data does not mean careless release. It means careful release with full context so results can be reproduced. Reproducible results are the core of reliable knowledge. A mature program also sets clear thresholds for decisions. A threshold is a criterion that says when to change course. For example, if repeated flybys detect organics in a plume at levels above a set limit, then a low-altitude capture mission is justified. If organics are not detected after many passes, then priority shifts to ice mechanics and ocean structure. If a lander detects simple organics but blanks show background at similar levels, then a deeper probe is not justified until cleanliness is improved. These are not rigid laws. They are guides that keep choices tied to evidence. They reduce the pull of hope and the risk of rushing. Risk management remains present in every step. Radiation dose must be budgeted. Shielding mass, science time, and fuel compete with one another. Routes through Jupiter's system must avoid the worst zones. Surfaces must be read carefully to avoid slopes, pits, and unstable crust. The maps built from earlier passes and from other missions are not decorations. They are tools that save lives and save instruments. They also make science better because they let us visit the places that matter with a plan that matches the ground. Work on Europa feeds other needs. Electronics that keep working after radiation hits can improve the safety of medical devices and power systems on Earth. Power sources that run steadily for years can support sensors in remote regions. Autonomy that handles delays and noise can improve vehicles and industrial controls. Methods for clean assembly, sealed interfaces, and strict tracking of parts can help drug manufacturing and food safety. Anchors and screws designed to grip hard ice without cracks can aid rescue tools and engineering in polar regions. Policy work on stewardship and on open data can strengthen cooperation beyond space. Future choices may include sample return. That is a serious step. It must follow clear gains from in situ work. It must follow proof that containment and quarantine can be done safely. Quarantine means holding a sample in a secure place where it cannot interact with the outside world until tests show it is safe or until it is studied under controlled conditions. The tests must be designed in advance and validated with mock samples. Facilities must be ready years before launch. If a sample return is ever approved, it will be because many lines of evidence say that the science return is worth the effort, and the risk can be reduced to a very low level. The integrated path is not a straight line. It bends as new facts arrive. It pauses when signals are unclear. It advances when evidence aligns. It balances new technology with proven methods. It values modest, reliable steps as much as bold plans. It treats null results as information, not as failure. A null result can mean that a plume is rare, that a ridge is sealed, or that organics are destroyed quickly near the surface. Each of these outcomes teaches us about the system and helps shape the next attempt. Across all of this, patience and care are the constant elements. Europa is cold, bright, airless, and bathed in radiation. It is also a place with deep water, with steady internal heat from tides, and with signs of salts and carbon at the surface. The ice moves under stress in ways we can model and test. Cracks and ridges open and close in time with a slow clock. Plumes may rise at times and carry samples within reach of spacecraft that fly by. Landers can touch the ice for short periods and report what they find if they are designed with honesty about limits and with respect for the place. An integrated program that links flybys, targeted sampling, short-lived landers, and later probes to shallow liquid can answer clear questions in a logical order. It can adjust based on what it learns. It can leave Europa as clean as it found it. Step by step, it can map how energy and matter move through the shell and into the ocean. Step by step, it can test whether chemical energy, water, and the right elements meet in ways that allow simple life. And even if life is not present, the knowledge gained will refine how we think about oceans that live in the dark under ice, and it will sharpen the tools and the laws we use to explore them with care.